everyone, I'm Michael. I'm the lucky Australian Paul alluded to who got to go back to Australia for Christmas and avoid a British winter. So I work in an area I like to call intelligent, self-actuating composite structures, which is my way of saying I make devices which move and move in some sensible way in response to some environmental or external stimulus. So what I think about, what the prototype we think about when we talk about these intelligent self-actuating structures is this. This is a photomorphing device that we received some funding from recently from the Leverhulme Trust. And we designed it to actuate, bend, to point towards the sun in response to sunlight or a light source. And it works like this. If we take a little quarter section and look at the internals, there's a light-sensing chemical component and a chemically sensitive actuating component. And the whole thing is designed so that when we bring these two chemicals together, we include the nonlinearities of the reactions, the diffusion rates, the saturation limits, and the geometry. We get something akin to a closed-loop proportional integral derivative controller, but it's chemical in nature, not electronic. If you want to find out a little bit more about this, come and see it at my poster, because I'm not going to talk about it today. Instead, I'm going to talk about the work which is grabbed the most of my attention over the last year, and that's been about getting the chemically sensitive actuating materials, these pH-sensitive hydrogels, to a point where they're practical to be used in an engineering application. So Anna's already talked a little bit about hydrogels. They're these wet polymers. I work with pH-sensitive hydrogels, so their state of swelling changes in response to the pH they're exposed to. And they have some desirable actuation qualities, one of which is softness, which is all the hype in robotics at the moment. Good strain, okay blocking stress, and this interesting property that they directly convert chemical energy into mechanical work, which opens up great pathways in terms of efficiencies and maybe some cool stuff to do with energy storage and transmission. However, there's always however, they've got some negatives as well. The last point on that list of negatives is something which the idea of the intelligent structures is trying to overcome. The points before that I'm going to talk about now, and it's what I've been trying to solve over the last year. How are we going to solve it? Of course, we're going to solve it by putting it in a composite material. So this takes the three-dimensional unconstrained swelling of the hydrogel, which is very difficult to put into application, and turns it into a targeted axial contraction. More than that, it increases the useful work output. In fact, if we look at the specific volume useful work output, we're getting something like a 2 orders of magnitude increase in that useful work output. The other point I've been looking at is toughness, which is something Anna also talked about. So this is a chart I stole from the University of Wollongong. This is essentially what the axes are saying. Working here, I tried to produce a few other hydrogels on my own from literature, and I couldn't get the balance right between having them mechanically robust enough to be used and giving me a decent swelling, a decent actuation output. So at my time at Wollongong this year, we worked on developing this new type of double network hydrogel. So I have a polyurethane network, which is the mechanical network, if you like, and the polyacrylic acid network, which is my stimuli sensitive network. So I can create these good swelling with good toughness still. The other big problem with hydrogels is they're not very well characterized from an actuation point of view. These have been made by scientists. The data they produce is not quite right for use in designing an engineering structure. So what we've done is something which I think is very Axis, very CDT, shows the interdisciplinary ethos of our group. I've taken an engineering technique, digital image correlation. I've taken it across the road to a chemistry lab, and we're using digital image correlation output in real time to control the titration of the material. And we get equilibrium results, swelling equilibrium results with higher resolution than I've ever seen before for a hydrogel. But behind each of those points, we also have kinetic data. Behind each kinetic data point, we have spatial data, which isn't very useful here, but as we go into composites, it will become more useful. At the moment, it just allows us to create a rather pretty video of hydrogel swelling. So this is digital image correlation happening in solution. And that's on a very soft material, and that's why this data has been so hard to get before. Another huge part of my work's been modeling, perhaps more specifically to create computationally cheap modeling that I can design these systems quickly with. And we've been using the characterization results and validation, and we get pretty good agreement at the moment between our modeling and our physical results. The next step is about improving power. So I say we can improve work output by incorporating them in a composite, but power is all about looking at reducing the dimensional units of the hydrogel. So we've been doing a lot of work at saying what's the right internal structure to put inside one of these devices, because you not just need to minimize the diffusion distances in the material, you need to make sure they stay minimized during loading. And we think the optimum might look a little something like this, which I know is hard to see. But what we've actually got going on here is we've got channels going through our hydrogel core and they're being coiled. And And this is where we are at the moment. I think this is sort of the state of the art in pH-sensitive hydrogels. We have a tough double network hydrogel where we've got a hierarchical structure to it for fast actuation. So we've got microchannels running through it and in a nanoporous stuff material. So with that, I'll conclude. I've got to thank the two research groups I'm part of, the multifunctional group here, and especially the FALL group over in chemistry, who look after an engineer that tries to learn something about chemistry. And a little shout out to the CDT 14s that are here as well. If you're interested in any of this actuation work, come and see me later today. We'll talk about some XPs, because I know Shafal in chemistry and Jonathan Roster in robotics are really keen to get some more projects happening in this area. So, any questions?